To address the issue of recurring electronics failures, begin with confirming the problem. Specifically, verify with the customer that their electronics are repeatedly failing due to overloads. Next, examine the surge protectors in use. Check that these devices are properly rated for the expected load, functioning correctly, and not overloaded themselves. Then inspect the electrical panel. Look for any signs of trip breakers, loose connections, or general overloads within the panel. Proceed to test the grounding and neutral connections. Verify that these connections are properly installed and tight within the electrical panel. Also, confirm that the grounding rod is properly installed and shows no signs of corrosion. Since direct inspection of the Romex inside the walls isn't feasible, you can use a non-contact voltage detector. Pass the detector along the outside of walls where the Romex is suspected to be stapled too tightly. If the detector indicates voltage, it could suggest a compromised Romex or a grounding fault. Also check for loose outlets and switches. Ensure that all outlets and switches are secure and not causing any shorts. To further diagnose the issue, monitor the circuit. Use an ammeter to monitor the current flow on the suspected circuit. Repeated current spikes could indicate a fault within the Romex. Consider environmental factors. Inquire if there have been any recent renovations, additions, or changes to the electrical system that could have potentially caused the problem. Investigate appliance usage. Ask the customer about their typical appliance usage. Abnormal current draws from appliances can overload circuits and damage electronics. Examine the circuit for electrical noise. Use a spectrum analyzer to check for electrical noise in the circuit. Excessive noise can interfere with the operation of electronic devices. Safety precautions are essential. Wear appropriate personal protective equipment, including gloves and safety glasses. Ensure that the power is disconnected before working on any electrical components. If you suspect a serious electrical issue, recommend that the customer contact a licensed electrician for further evaluation and repair. The investigation should follow a logical sequence. Firstly, confirm the customer's complaint of repeated electronic failures due to overloads. This establishes the problem and its frequency. Secondly, thoroughly inspect the surge protectors being used. Confirm they are appropriately rated for the devices they are protecting, are functioning as intended, and are not themselves overloaded. A malfunctioning or inadequate surge protector won't provide the necessary protection. Thirdly, carefully examine the electrical panel. Check for any trip breakers, loose wire connections, or signs of overheating. Trip breakers indicate overcurrents, while loose connections can cause arcing and voltage drops, both harmful to electronics. Fourthly, test the grounding and neutral connections within the electrical panel. Verify that all connections are secure and meet the required electrical codes. A poor ground or neutral connection can lead to voltage fluctuations and equipment damage. Fifthly, address the customer's concern about the Romex wiring. Since visually inspecting the wiring within the walls is impractical, use a non-contact voltage detector along the suspected areas. Any detected voltage could indicate damaged insulation or a compromised wire. Sixthly, inspect all accessible outlets and switches on the affected circuit. Ensure they are properly wired, securely mounted, and show no signs of damage or overheating. Faulty outlets and switches can create shorts and voltage irregularities. Seventhly, monitor the current flow on the suspected circuit using an ammeter. Record the current draw under various operating conditions and look for any unexpected spikes or fluctuations which could indicate a wiring fault or an overloaded circuit. Eighthly, inquire about any recent changes to the electrical system such as renovations or new appliance installations. These changes could have introduced new electrical loads or wiring errors. Ninthly, gather information about the types of appliances and electronics being used in the affected circuit. Determine their power consumption and usage patterns to identify any potential overloads or compatibility issues. Tenthly, use a spectrum analyzer to check for electrical noise on the circuit. High levels of electrical noise can interfere with the operation of sensitive electronic devices. The use of an ammeter is crucial for determining the actual current draw on the affected circuit. Connect the ammeter to the circuit and measure the current under different operating conditions. This will reveal whether the circuit is consistently overloaded or if the overloads are intermittent. Pay close attention to the current readings when various appliances and electronics are in use. This will help pinpoint the sources of the overloads. If the current readings are consistently high, it may indicate that the circuit is simply undersized for the load. In this case, consider upgrading the circuit to a higher amperage rating. If the current readings fluctuate erratically, it may indicate a loose connection or a wiring fault. Investigate these possibilities further. Electrical noise can disrupt the functioning of sensitive electronic devices, causing them to malfunction or fail prematurely. A spectrum analyzer is a specialized tool used to measure the amplitude of electrical signals across a range of frequencies. By connecting a spectrum analyzer to the affected circuit, you can identify the presence and intensity of any electrical noise. Common sources of electrical noise include nearby appliances, motors, and fluorescent lighting. If excessive electrical noise is detected, consider installing a line filter to reduce the noise levels. This can help protect electronic devices from damage. Grounding and bonding are critical for electrical safety and proper equipment operation. The grounding system provides a path for fault currents to flow back to the source, tripping the circuit breaker and preventing electrical shock hazards. The bonding system ensures that all metallic parts of the electrical system are at the same electrical potential, reducing the risk of shock. To test the grounding system, use a ground impedance tester to measure the resistance between the grounding electrode and the electrical panel. The resistance should be low, typically less than 25 ohms. To test the bonding system, use an ohmmeter to measure the resistance between various metallic parts of the electrical system, such as metal conduits, junction boxes, and equipment enclosures. The resistance should be very low, ideally less than 1 ohm. The NEC, or National Electrical Code, provides comprehensive guidelines for electrical installations. This code addresses safety standards such as proper wiring, grounding, and overcurrent protection to prevent hazards like electrical shocks and fires. Specific sections of the NEC, such as Article 250 for grounding and bonding and Article 210 for branch circuits, offer detailed requirements that must be followed to ensure a safe and compliant electrical system. Familiarity with the NEC is essential for any electrician or electrical worker. The NEC is updated every 3 years to reflect changes in technology and best practices. Overloaded circuits can cause overheating, which can damage wiring, insulation, and equipment. Overheating can also lead to fires. It is important to identify and correct overloaded circuits as soon as possible. There are several ways to identify an overloaded circuit. One way is to check the amperage rating of the circuit breaker and compare it to the total current draw of the devices connected to the circuit. If the total current draw exceeds the amperage rating of the breaker, the circuit is overloaded. Another way to identify an overloaded circuit is to use a thermal imaging camera. This camera can detect areas of excessive heat, which can indicate an overloaded circuit. If you suspect that a circuit is overloaded, take steps to reduce the load on the circuit. This may involve disconnecting some of the devices connected to the circuit or moving some of the devices to another circuit. It may also involve upgrading the circuit to a higher amperage rating. Surge protectors are designed to protect electronic devices from voltage spikes. However, surge protectors can only handle a limited number of surges. After a surge protector has absorbed several surges, it may no longer be effective. It is important to replace surge protectors periodically, especially after a major electrical event such as a lightning storm. There are several types of surge protectors available. Some surge protectors are designed to protect the entire electrical panel. Other surge protectors are designed to protect individual devices. When selecting a surge protector, it is important to choose one that is appropriate for the devices you are protecting. The non-contact voltage detector is a valuable tool for detecting voltage without making direct contact with the wires. This tool is particularly useful for checking for voltage in hard-to-reach places or in situations where it is not safe to make direct contact with the wires. To use a non-contact voltage detector, simply hold the detector near the wire you want to test. If voltage is present, the detector will light up or make a sound. The non-contact voltage detector is a safe and easy way to check for voltage. However, it is important to use the tool properly. Always follow the manufacturer's instructions. Be aware that non-contact voltage detectors may not be accurate in all situations. The readings can be affected by factors such as the distance from the wire, the type of insulation, and the presence of other electrical fields. When using a non-contact voltage detector, it is important to exercise caution. Do not assume that a wire is de-energized just because the detector does not indicate voltage. Always use a qualified electrician to verify that a wire is de-energized before working on it. The use of personal protective equipment, or PPE, is essential when working with electricity. PPE can protect you from electrical shock, burns, and other injuries. Common types of PPE include gloves, safety glasses, and insulated tools. It is important to choose PPE that is appropriate for the task you are performing. For example, when working with high voltage, you should wear gloves that are rated for the voltage you are working with. It is also important to inspect PPE regularly to ensure that it is in good condition. Do not use PPE that is damaged or worn. Always follow the manufacturer's instructions for the use and care of PPE. The NEC Table 310.15b16 provides ampacity ratings for conductors based on their size, insulation type, and installation conditions. This table is used to determine the appropriate conductor size for a given circuit. The ampacity of a conductor is the maximum amount of current that it can carry safely without overheating. The ampacity of a conductor is affected by several factors, including the size of the conductor, the type of insulation, and the installation conditions. Larger conductors have a higher ampacity than smaller conductors. Conductors with higher temperature insulation ratings have a higher ampacity than conductors with lower temperature insulation ratings. Conductors that are installed in free air have a higher ampacity than conductors that are installed in conduit or buried underground. The NEC Table 310.15b16 provides ampacity ratings for conductors under various conditions. When selecting a conductor for a circuit, it is important to choose one that has an ampacity that is sufficient for the load. It is also important to consider the dating factors that may apply to the conductor. Dating factors are used to reduce the ampacity of a conductor when it is installed in certain conditions. For example, a conductor that is installed in a hot environment may need to be derated to account for the increased temperature. It's imperative to maintain a safe working environment when dealing with electrical systems. Always de-energize circuits before beginning work and verify the absence of voltage with a reliable tester. Employ lockout-tagout procedures to prevent accidental re-energization. Use insulated tools and wear appropriate personal protective equipment, including safety glasses and gloves. Be mindful of your surroundings and avoid working in wet or damp conditions. If you are not comfortable or qualified to perform a particular electrical task, seek assistance from a licensed electrician. Proper wire sizing is essential for electrical safety and efficiency. Undersized wires can overheat, causing insulation damage, fires, and voltage drops. Oversized wires are more expensive and can be difficult to work with. The appropriate wire size depends on the amperage of the circuit, the length of the wire run, and the type of insulation. The NEC provides tables that specify the minimum wire size for various applications. Always consult the NEC and follow its guidelines when selecting wire sizes. When working with electrical panels, it is essential to maintain a safe working distance. This distance is typically 3 feet or more, depending on the voltage of the panel. The safe working distance provides a buffer zone in case of an arc flash or other electrical incident. Keep the area around the electrical panel clear of obstructions and ensure that there is adequate lighting. Never work on an electrical panel alone. Always have a qualified assistant nearby in case of an emergency. When dealing with aluminum wiring, it's important to exercise extra caution. Aluminum wiring is more susceptible to corrosion and loosening than copper wiring. Use only connectors that are specifically designed for use with aluminum wiring. Apply an antioxidant compound to the aluminum wiring before making connections. Regularly inspect aluminum wiring connections for signs of corrosion or loosening. If you find any problems, tighten the connections or replace the connectors as needed. Aluminum wiring requires special attention to ensure safe and reliable electrical connections. The proper use of conduit is essential for protecting electrical wiring. Conduit provides a physical barrier against damage, moisture, and corrosion. There are several types of conduit available, including rigid metal conduit, electrical metallic tubing, and flexible metal conduit. The type of conduit used depends on the application and the environment. Always follow the NEC guidelines for the installation of conduit. Ensure that the conduit is properly supported and secured. Use appropriate fittings and connectors to make watertight and secure connections. Proper conduit installation is critical for electrical safety and long-term reliability. Ensuring proper box fill is critical for preventing overheating and ensuring safe connections within electrical boxes. Overcrowded boxes can lead to insulation damage, loose connections, and potential fire hazards. The NEC provides guidelines for calculating box fill based on the size and number of conductors, devices, and fittings within the box. Always follow the NEC guidelines when determining box fill. Use larger boxes if necessary to accommodate the wiring and devices safely. Proper box fill is essential for electrical safety and preventing problems down the road. Performing voltage drop calculations is essential for ensuring that electrical equipment receives adequate voltage. Voltage drop occurs when electricity flows through a wire, causing a reduction in voltage at the load end. Excessive voltage drop can cause equipment to malfunction or fail prematurely. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Use voltage drop calculators or consult the NEC to determine the appropriate wire size for a given circuit. Consider the length of the wire run, the amperage of the circuit, and the type of conductor when performing voltage drop calculations. Correcting voltage drop can improve equipment performance, reduce energy waste, and prevent costly repairs. When dealing with three-phase power, it's important to understand the voltage relationships between the phases. In a typical 208/120 volt three-phase system, the voltage between any two phases is 208 volts, while the voltage between any phase and neutral is 120 volts. In a 480/277 volt three-phase system, the voltage between any two phases is 480 volts, while the voltage between any phase and neutral is 277 volts. Use a voltmeter to verify the voltage relationships in a three-phase system. Ensure that the voltage is balanced between the phases. Unbalanced voltage can cause equipment to overheat and fail. Proper understanding of three-phase power is essential for working safely and effectively with electrical systems. When troubleshooting electrical problems, it is important to use a systematic approach. Start by gathering information about the problem. Ask the customer questions about when the problem occurs, what devices are affected, and what has been tried so far. Next, perform a visual inspection of the electrical system. Look for any obvious signs of damage or loose connections. Then, use a multimeter to measure voltage, current, and resistance. Compare your measurements to the expected values. Use a wiring diagram to trace the circuit and identify potential problems. Finally, use your knowledge of electrical theory and your experience to diagnose the problem. A systematic approach will help you troubleshoot electrical problems quickly and efficiently.